I am Professor Dean Aslam from Michigan State University, and I'm here at the 2013 MRS Spring Meeting to present my outreach modules, which are called Functional Bricks with Embedded Intelligence. And I have several examples that I would like to show. The first one is a module made out of Legos or Lego-like blocks that explains nanotechnology. And the way it does is I drive a big gear with a small gear, and that means that the small gear is moving faster than the big gear. So if I drive big gear with a small gear and then continue this, then the motion becomes slower and slower. So I want to demonstrate that. I have a 9-volt battery, and I connect it to the motor. And so the first gear is moving with a certain speed, and then it is attached to a small gear which drives the big gear, and then this process continues because the small gear is driving a big gear, so the motion is slowed down. So this is moving faster than the next one, and that is moving faster than the next one, and so on. So all these gears are moving, but they don't appear to be moving because some of them are moving very, very slow. Now, one day I was making a presentation to a second grader, and I told him that all gears are moving. But he said that in his opinion, this gear is not moving. I said, it's moving very slowly. He said, no, I don't see it moving. So how do I explain that to a second grader? And it took a few weeks for me to find out a way to explain it to a second grader that actually all gears are moving. The middle one is also moving. So this is what I did. I built another gear train which looks like this. In this case, I slowed down from gear 1 to gear 5, and then I make it faster. I speed up. And this is the demo that I can explain more. So you see that this is the fastest moving gear. It slows down, and then the green gear is very slow. It's hardly moving. But then I reverse the process, which means I speed up. And you can see that this gear is moving at the same speed as the last one. And the green gear appears to be moving with almost no speed. It's not moving. So I showed the second grader. I said that now tell me whether the green gear is moving or not, and he said it should be moving because otherwise this gear will not be moving. So that's about one. This is a Lego-based Van de Graaff generator that generates high voltage by creating static charges, and I want to show a demo of how to detect that charge. This is a sensor which can find out whether the charge is positive or negative. If the charge is positive, then this light will light up, and if it's negative, then this one will light up. So let's see which one lights up. So this shows that it is a positive charge. So if I bring my hand close to that, I get a little shock, a little spark. This Lego-based Van de Graaff generator is very interesting because the learners can build it themselves using Lego pieces. So I want to show different parts of this Van de Graaff generator. So this is the globe, and I take it out, then it has 2 pulleys. This is the upper pulley is made out of leather, the top surface. The lower pulley is made out of Teflon. So this generates positive charge and this generates negative charge. So there's a separation of charges, positive here, negative here. This is the negative charge, and this is the positive charge that is picked up by these wires. And if I put a globe on top of that, the charge accumulates on the globe. So this is how it works, and it is driven by a robotic controller, so the learners can change the speed of the lower pulley, and they can also study different components such as They can use different pulley materials, different belt materials, and different lower pulley materials. So this is an interesting way to study control and materials and static charges. This is a Lego robot driven by a chip called microcontroller and 2 batteries. It has homemade sensors, and one of the sensor is a light sensor that can track the black line. So let's see a demo. So I position it on the black line, and then I switch it on. So it is thinking where is the black line, where is the white line, and start following it. So if I kind of try to mess it up, so it should ultimately find the edge of the black line and start following it. See that? So this robot, as compared to others in the market, will be very inexpensive. We are planning to market it for under $50. And it's a programmable robot and can be programmed in a language called C using a very inexpensive programmer and compiler. I want to explain one more thing about this line follower robot, and that is I have used a Lego plate like this to build the electronic circuits, and you can see it here. This is the microcontroller, that's the brain of the robot, and these are different connections here all the way to the battery as well as to the sensor, and these wires are running around, and I had to make some changes by machining in the Lego plate. But the next generation of this robot will use an inkjet printed plate, which will have holes for mounting the socket where we mount the microcontroller, and there will be other holes for other parts of the circuit. And this is inkjet printed, and there is some metal layer that is deposited using microfabrication. So this is for the first time that there is a combination of metal layer and inkjet printing, building a complete circuit board. This is Bob Jesko, who has a remarkable capability to increase his attention level and decrease his attention level. And this is a robot which moves if he is highly focused or he increases his attention level. Let's see a demo. I'm going to switch it on. Yeah, he did defocus, yeah.
Oh, I see how to do it now.
Yeah.
Okay, watch.
Yeah. Very good. Oh, look at this. Oh, he's doing it on demand. See that?
I'm scaring myself. Is it on? Okay.
So you got a piece of dirt here somewhere. Is there dirty here or something here? Oh, so I tried. So I think that should be.